Welcome everyone to today's tutorial. Today we'll be talking on matrix. In matrix, the plural of the word matrix is matrices, whereas the singular is matrix. So a matrix is a rectangular array of numbers that are enclosed within a bracket. So first of all, we take note of this word, a rectangular array of numbers. When you have numbers that are arranged in a rectangular manner, I have 2, -5, 0, 1, 7, 3. If you try to draw lines to enclose these numbers, you find out that you have a rectangle at the end. Or if I have 1, 4, 3, this is also a rectangle. So it's a rectangular arrangement of numbers 1, 3, 10. I can also have something like 2, 1, 4, 0, 8, 7, 6, 3, 2. In this case, this is a square. It's also the kind of matrix we talk about. It's called a square matrix because in matrices we take notes of the rows and columns. The rows are these numbers in the horizontal pattern. So we have 1, 2, 3 rows, and then we have the columns here also 1, 2, 3. So a matrix is ordered in rows and columns. In most cases, we use M to represent the rows and N to represent the columns. Okay, so I'm going to finish up that definition of matrix. Then the next thing we said that are enclosed within a bracket. So instead of using a square or a rectangle to enclose them, we enclose it in a bracket. We enclose them in a bracket. So this is basically what matrix is. Now we have some terminologies used in matrix. We have the elements of a matrix. Elements are the individual numbers that we can get in a matrix. So all these are the elements 0, 8, 7, 2, 3, 6 are all elements of a matrix. Then the next thing we want to talk about in the matrix, in what case a matrix, or in what case can we say a set of matrices is equal? So if I have two matrices here, let me use letters to represent them. A. Now if you look at my subscript, I'm using numbers. I'll tell you in a moment what these numbers are used, which you also see in most textbooks and learning materials that talk about matrix. These 2, 3. Now, when we try to get the position of an element in the matrix, we use the position of each row and column. For example, this is the first row, this is row 1, and then this is row 2. So you can see the rows appear in the first position here, 1, 1, 1, and then this row 2, row 2, row 2, row 2. So if I pick this element out, it means that this element A, once we see these two as its first subscript, we know that this element A occurs in the second row, and then the second subscript represents the position in the column order. So we have column 1, column 2, and column 3. So we see it here. So this one represents column 1, column 2, and column 3. And therefore, this is an element A in row 2 and it's in column 2. So we have 2, 2. So that's one way we can use to represent the position of an element in a matrix. Back to what I was saying about equality of matrix. When two matrices are equal, it means that the order or the size is equal. So say two matrix A, and take note, matrices are usually labeled with capital letters. So this is a matrix A, and I have another matrix here, B equal to B, B, B. Now these are all in row 1. This is the second row 2, and then we come with their column 1, column 2, column 3, column 1, column 2, column 3. So say two matrices A is equal to B. This happens when their order are equal and each element in their respective position is equal to the corresponding elements in the second matrix. Alright, so I believe you understand what that is instead of writing. So this actually means this will be equal to this will be equal to this. That's the elements that are in their respective position. All these elements in their respective position are equal to the elements in the second matrix that corresponds to the position that they occupy. So that's quality of matrix. And I also told us about square matrix. When the number of rows is equal to the number of columns, that's the square matrix. And then we have the principal diagonal. Now, if I have a square matrix, which is one crucial factor that a principal diagonal can occur. If I have this matrix A, 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 and A, of course we can label their positions. So this is 1, 1. Okay, this 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, and 3, 3. Okay, I'll just make that elaborate and clear so that we can see it. So this is a square matrix, and when we want to pick out the principal diagonal, if you have a square, let me say this is a square. Now this square that I just draw now, you can deduce its diagonal, or you can know the diagonal by a straight line. A straight line that runs through from this point to another point. Okay, let me delete that. I'll just make use of my normal sketch here. So I have this, let me assume this is square. So the diagonal will run from one of its edge to the opposite edge. Okay, so the numbers that run from here to the opposite corner, then take out all these numbers: A11, A22, A33. So this is the principal diagonal. Then if we can also talk about secondary diagonal, that's the second part of the diagonal, which is this. And that's A13, A22, A31. So this is the secondary diagonal. What is the primary or principal diagonal? I'll be making use of that, especially in upper classes when asked to find a triangular matrix. Triangular matrix simply means, in this case, I have these numbers. The numbers below the principal diagonal. Let me make this work a little bit neat. So if I have, write 7. So we know that this is the principal diagonal of this matrix. So every other number below this principal diagonal, to have a triangular matrix, we are going to draw a triangle beneath the principal diagonal. So I'm going to have this. I'm going to have this a triangle. Okay, it means every other thing here is going to be 0. So when we have zeros occupying each of these positions, of course, that's a triangular matrix. Let me clear out more spaces onto that again, so that I'm sure that we understand this whole thing. I'm gonna wipe all this. So I can do that again, and then we see what I'm talking about. Okay, so if I have a matrix like this, 7, 2, 1, 8, minus 5, 4, 3, 2, 1. Of course, we know that this is the principal diagonal. So if we want to have a triangular matrix, we'll manipulate this matrix in such a way that these numbers beneath the principal diagonal will be 0, 0, 0, 0. So this is a triangular matrix, specifically called a lower triangular matrix. But if we still have something like this, we have probably quite different: 7, 2, 1, 0, 6, minus 1, 1, minus 5, 4. This is another matrix, and then we want to find the upper triangular matrix. Then that means all the entries above the principal diagonal will be 0. All the numbers above the principal diagonal will be 0. So I have 0 here, 0 here, and 0 here. I believe you understand what this says. And so this is the lower triangular matrix where the zeros occur below the principal diagonal, and this is the upper triangular matrix where the zeros occur above the principal diagonal. Then we have null matrix. Null matrix occurs where all entries are 0. This is a null matrix. Of course, we now have to get the transpose of the matrix. The transpose of a matrix. The transpose of a matrix simply means if we have a matrix, let me see, 2, 1, 3, 5. This labeled A, and we have to find the transpose, which is denoted by a little t on top. That's equal to that's interchanging the rows and column. So this is the row 1, this is the row 2. So the rows will be interchanged with the column. So this is going to be 2, 1, and 3, 5. So the transpose of a matrix, like I said earlier, is simply done by interchanging the rows and column. If I have a matrix A equal to 3, 6, 4, 2, 9, 8. The transpose I'm going to get will be the reverse of the order of this matrix. This is a 3 by 2, 3 rows and 2 columns. So the transpose will be 2 by 3. So this row will become a column. I'll have 3 and 6. This row will become a column, 4, 2. And this row will become a column, 9, 8. So this is our result. Then I'm going to talk about symmetric matrix. But if I talk about symmetric matrix, let me give you this so that you can get the transpose of this matrix. So I want you to get the transpose of this matrix. Pause the video and then when you actually play it back to see the result. So the transpose will simply be done by interchanging these rows and the columns. So 2901, we'll change it to a column and that'll be this 2901 minus 5 minus 11, 6, 3, and then 1, 2, 7, 4. So that's the transpose. Then I'm going to talk about symmetric matrix. So we can also see here that this is a 3 by 4. Now it's now a 4 by 3 in its transpose. So a symmetric matrix is a matrix that is equal to its transpose. So if I have a matrix B and this B is 5, 4, 4, negative 2. If I have the transpose and they are equal, then B is a symmetric matrix. So I'll change this row to a column, 5, 4. I'll change this row to a column, 4, negative 2. So we can see that they are the same. The transpose and the original matrix are the same. Okay, if I have another example, matrix D. One idea about symmetric matrix is that the entries above and beneath the principal diagonal are the same. If they are the same, then that's a symmetric matrix. What do I mean by that? First of all, I'm going to put in my entries for the principal diagonal. Let me put in some numbers here: 9, 0, -6. You can see this is the principal diagonal. It runs from one corner to its opposite corner. Now I'm going to put entries above and beneath that are the same. So I'll start with here 1, 1, 2, 2, 3. Okay, I think these two supposed to be here, and then 3, 3. So each of the entries are the same. Opposite entries are the same. Okay. So if I have the transpose of this matrix, 9, 1, 2, 1, 0, 3, 2, 3, -6. So it's as if we are just repeating it, but actually the transpose of D is this and they are the same. So the idea is that if you have different numbers as their principal diagonal, it can be 1, it can be 10, it can be 12, it can be anything else. And we know that the next place to fill is here, 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 here. I'm going to try to make my work look neat so that we understand it. What I'm trying to say. I have those same numbers: 1, 10, 11. We know that a number should be here, a number should be here, a number should be here. In other words, symmetric matrix works with a square matrix that has same rows and same column. So if I replace these missing entries with same numbers, 2, 2, 5, 5, 0, 0, the entries above and beneath the principal diagonal are the same, then I'll have a symmetric matrix. So let me talk about the next thing: skew symmetric matrix. Skew symmetric matrix. A matrix is said to be a skew symmetric matrix if its transpose is opposite to its negative. And now in this case, I'll use this one to explain that concept. I'll use this example to explain that concept. Now let's suppose that in this original matrix D, the entries above the principal diagonal, okay, I'm going to leave this principal diagonal 1, 10, and 11. I'm going to leave them the same, and I'm going to make the entries above and beneath it have opposite signs. So if this is -2, here will be +2. This is +5, here will be -5, and 0 has no signs because it's just 0. So as we said, the transpose is equals to its negative. So if we transpose this matrix, we'll have 1, -2, 1, -2, and 5. 2, 10, and 0, 5, 0, and 11. So this matrix is equal. Oh, something I forgot to let us know is that in a skew symmetric matrix, the principal diagonal must be all 0. There must be 0. Each entry must be 0, because that will make us have our required results. Each entry must be 0. When all entries in the principal diagonal are 0, we'll have what it actually defines skew symmetric matrix as. So you can see that I'm going to permit me to start this process all over again, and in a more clear manner, so we can understand it fully well. So I'm going to have a matrix. In most cases, you might not be asked to find a skew symmetric matrix, but for the purpose of knowledge, I think it's important that we have a basic idea of what skew symmetric matrix talks about. So first, I'm going to make my principal diagonal everything 0, and then the entries up and above my principal diagonal. So the next thing I'm going to do, the entries up and above the principal diagonal will have opposite signs. So if this is minus, here should be plus. If this is plus, here should be minus. I can just choose them the way I want them to be, minus, plus. So the transpose of matrix D will be 0, -5, 1, 5, 0, -2. I'm changing all these rows to column, -1, 2, and 0. So we can see that each of these entries has opposite signs, but they are the same. -5 here is in D, and 1. So you can see 0 has no opposite sign, it remains 0. -5 here, the opposite is 5, 1, the opposite is -5, 5 here, the opposite is -5, 0, 0, -2, 2, -1, 1, and so on and so forth. So that's it on skew symmetric matrix. So I believe I've been able to take us through the different terminologies we use in matrix. Okay, so thanks for watching this tutorial.